Welcome to the solutions for the Regents Physics Measurement in Vectors problem set numbers 12 and 13. Let's get started with number 12 here. Graphically find the sum of all the following pairs of vectors whose lengths and directions are shown below. We're given 6 different vectors here with varying lengths, which are in parentheses, and directions as indicated by the arrowheads. All right, we need the sum for A of vector D and vector A. Vector D and vector A are at 180 degrees to each other, which would produce a minimum resultant. It's obvious, should be obvious to us, that minimum resultant would be 1 unit. And because the 4-unit vector D is greater than the 3-unit vector in A, for vector A, the direction ends up being the original direction of vector D, which is at 0 degrees. So 1 unit at 0 degrees. Vector C and vector D are at 0 degrees to each other. That means their magnitudes combine and produce a maximum value. And so the resultant for choice B here would be a vector that is 10 units long, and both vector C and vector D are at 0 degrees. So the resultant would also be at 0 degrees. Vector C and vector A are at 180 degrees to each other. So that would produce a resultant that is 3 units in length, producing a minimum. We subtract. And vector C has greater magnitude than vector A, and vector C is pointing at 0 degrees. So the resultant would end up being pointed at 0 degrees as well. Notice all our answers have magnitude and direction, very important. Vector E and vector F both have the same magnitude and are at 180 degrees to each other. In other words, they're pointing in the opposite direction of each other. And because they have the same magnitude but pointing in opposite directions, there would be no resultant here. You wouldn't have a resultant. So the answer is 0. All right, lastly for E, we have vector B, which is up in the positive y direction for 3 units. And vector D, which is in the positive x direction for 4 units. We were asked to find the resultant of this. The resultant is always where you end up relative to this, where you started from. So we label this R. And what we're going to do here, in this case, these 2 vectors are at 90 degrees to each other. And so we're going to give ourselves a rectangular coordinate system here by which we can use to find the resultant R. Because these 2 are at 90 degrees to each other, this allows us to use trigonometry to solve the problem, because the 3-unit vector, the 4-unit vector, and the resultant itself form a right triangle. So how would we find R? R squared equals 3 squared plus 4 squared using Pythagorean theorem. So R squared equals 9 plus 16, which is 25. Take the square root of both sides, and R equals 5 units. You might remember from your study in geometry or trigonometry, this is a special triangle called the 3, 4, 5 triangle. All right, next we want to find this angle that I'm marking here as theta. theta, T-H-E-T-A, is the Greek letter lowercase version of this. That's the symbol that we use to indicate angles. We'll use that all year long in physics. Well, how do we find theta? Our 3-unit vector over here would be the same as this dotted line. The x-axis itself is the same as the 4-unit vector. What trig function relates the angle we're trying to find, the given 3 units, and the given 4 units? Well, the 3 units are opposite the angle. The 4 units are adjacent to the angle. And so that sounds to me like we would use tangent. So tan of theta is 3 over 4, opposite over hypotenuse. Well, how do we find the angle theta itself? That gives us the tangent of the angle. How do we find the angle itself? Well, we would do what's called take the inverse tangent of both sides. So theta is the inverse tangent of 3 over 4. So go ahead on your calculator, making sure you're in degree mode, and take the inverse tangent of 3/4, or 0.75. And I believe we would find that angle to be 37 degrees, 2 digits. So our final answer here is that the resultant would be 5 units at 37 degrees with respect to the rectangular coordinate system that we have outlined in this problem. Okay? So that's how you handle when vectors are at 90 degrees to each other. Moving on to 13, we have an airplane that flies at 200 kilometers per hour with respect to the air. What is the velocity of the plane relative to the ground if it flies with A, a 50 kilometer per hour tailwind, and B, a 50 kilometer per hour headwind? Well, the plane flying 200 kilometers per hour with respect to the air is literally how fast it's traveling in the air. However, with tailwind, headwind, or crosswind, this is not what a person that's standing on the ground would see. So for A, let's just sketch this out. For A, we have, let's say the plane is flying in that direction at 200 kilometers per hour, and the plane experiences a 50 kilometer per hour tailwind. Okay? What I'm going to do here is I'm going to move things a little bit. Suppose this is the 200 kilometers per hour, and the plane experiences a 50 kilometer per hour tailwind. That means the wind is traveling in the same direction as the plane, or in other words, pushing on its tail. Well, what would the resultant here be? Well, as you can see, these two vectors are at 0 degrees to each other, producing a maximum value. And so the resultant speed of the plane would be 250 kilometers per hour. For B, we have the plane once again at 200 kilometers per hour. But this time, the plane experiences a 50 kilometer per hour headwind. Well, that means the wind is blowing at the nose of the plane in the opposite direction of the motion of the plane. Here we can clearly see that we have two velocities that are at 180 degrees to each other. This would produce the minimum value of these two vectors. And so our resultant would be that the plane would only have a net speed, or a speed relative to the ground, of 150 kilometers per hour. All right, I hope this has helped introduce some of the concepts and problems with regards to vectors. We'll have a nice problem that we'll tackle together in class tomorrow.